Okay, welcome back, everybody. Good to see that two you showed up. Um, we had a long break, and we're gonna have another break. Obviously, next Friday is Thanksgiving, so we won't have class next Friday. Basically, what we have left over is I'm sure you've been following, obviously, chapter 14, which I'll complete today. We'll knock that out, and then probably touch on 15 a little bit because that's really short. And then when we come back after Thanksgiving, we would probably finish it up, both 15 and 16. 16, I was asked the question if that was optional. 16 is part of the curriculum. However, it will not be on the final exam. There is homework for it. So it's not in the final because when we get to it, we're so close to the end of the semester. I just found it best just to leave it out and just cover chapters 1 through 15, but still have homework for it. All right. There are some, I don't believe both of you have that, but if you do have any assignments that are missing, recall that I did mention that yes, you can still turn them in. However, there will be a penalty involved with it. Okay, Canvas will calculate it. Now, for the homework, some of you may have just done one attempt. There's two attempts per homework, and we're happy with that grade. Way back when, let's say chapter one, chapter two. But let's say, for example, you want to redo it because you didn't do your second attempt. By all means, it's still open. You can go back and do the homework, previous homeworks, and do a second attempt. Now, um, Canvas will think that it is being done late, so it would implement a late penalty. However, I did state this, and I'll repeat it again, that if the original submission was done, at the due date, and you come back, weeks later to do the second submission to get a better grade, I'm more than happy to remove the penalty on your second submission if you did submit it when it was due. Okay, so, oh, excuse me, my dog's in the background barking at something. All right, and everything else except the exams are doable until the last day of the semester, which is September 16th, I believe. Let me double check that. Yeah, the 16th of December. That day, everything gets, uh, Canvas shuts the course down. Also, remember that the final exam is all comprehensive. It's about 60 questions. It is timed 110 minutes, I believe, almost 2 hours, 110 minutes. And but it is due that day. It's unlike the other exams that we let it run through the weekend. The final exam is not. So check your schedule, work schedule, whatever schedule you have to work with. Make sure that you have that day open up for you to knock that out. And I can move the day forward a couple of days if you need to, based on your schedule. I have no problem with that, but I cannot move it after the 16th. Okay, so keep that in mind. Let me see what else. On my Tuesdays and Thursday classes, my 1 o'clock and my 4:15, they are also in about the same pace with respect to chapters. But on Thursdays, those two times have been set up for what are called study days, self-study days. So we don't have lecture. Feel free, if you have any questions, to come to those days on Thursday with any questions that you may have. We can go over it because all three of my classes, you guys and my two GCC are using the same textbook, the same format. The only difference is that you guys have the additional lab. They and GCC, the lab is a separate course in itself. Okay. But everything else with respect to lecture is the same. So feel free. You're welcome to come on Tuesdays. Tuesdays will be the remainder of the chapters. They are in chapter 14, roughly about halfway through. And I'm going to be doing lectures on Tuesday to the end of the semester. And then Thursdays will be the study days. We will probably have one here, maybe the last meeting that we have on the 9th. It all depends how far along we get with the chapters here. So anyway, so keep that in mind. If you have any questions, and bring them in. I'm sure, regardless of you guys being an SCC or GCC, the questions should be same topic, the same book, same everything. Except the exams. Exams are slightly different. Yeah, same type, but different. Okay, any questions? Any questions you may have? Oh, am I breaking up? Let me check my speaker to make sure see what's going on here. Okay. Bear with me for a second. Sometimes my audio okay. All right. Debbie, am I still breaking up to you? How about Grace? And did I pronounce that right? I'm sorry, Riwaya. Okay, Grace, you're okay. It's off and on, off and on. Okay, well let me shut down some of my some things I may have on the background. So bear with me. Okay. All right. My connection's doing okay. Okay. I'm going to switch over to my extended Wi-Fi. So we might cut out for a second, but it's a little bit stronger signal. Okay. I'm connected and got a little bit stronger signal. CPU. Okay. Okay, I'm closing some stuff in my background, so it might make things a little better. Okay, I'm in the blue with respect to memory and CPU, and my signal strong. All right, not better, Debbie? Good. Okay, probably I had so much stuff going on in the background. Normally I shut that off, and I forgot to do it this time. Yeah, everything here showing me in blue. I got Zoom has an area where you can go in and check your memory and CPU and your connection. Everything's in blue. It was in red. All right then. So, all right, good to hear everybody can hear me okay. So, any questions about what we got left over to do? The semester is very quick coming up on us here. Next semester I'm going back on campus. We're trying to slowly phase out the online pros and cons with respect to online. I was kind of skeptical with this online, and I look at my grades with online. I have over 1,000 students who've been doing the teaching here at Maricopa Community Colleges, and I keep all the scores and everything, and I plot my data on. When I look at the overall average score of pre-COVID versus now, I see very little difference, in that. So anyway, but some people don't like the Zoom or the video. All right. Yeah, for some people, I see that this is going to be here to stay. I don't think Maricopa has really grasped that because, last semester we were on the trip to Kansas City, and the advantage from an instructor was I can teach from any place. In fact, I was in Middle New Mexico teaching my class. Stopped at a park so I can do my class. So one advantage from my end of it. Okay, well, I tell you what, any other questions, comments, concerns? I will jump into chapter 14. And what this chapter deals with is we're going to try to put everything together. I mean, let's stop and think about what we have been doing since we started. The first semester, the first chapters, we introduced the chemistry a little bit about what to expect, kind of a preface of what's going to happen. We got into a chapter of calculations and conversion factors that we use a technique to help us in the chemical calculations. We start talking about the atoms, okay? And then from there, kind of how the atoms are put together with respect to the subatomic particles of the proton, the neutron, and then the electron. And then we talked at length about how the electrons are have wave character, light character, and behave like light. And it turns out that these electrons actually exist in quantized, what are called quantized energy levels, very specific energy levels. And actually talked about the orbits. And that kind of led us into when we talked about valence electrons and how many valence, the outermost electrons these atoms have. And we stuck specifically with the A transition metals, so group 1 through 1A through 8A. And the B's were kind of more, we can't predict as far as their respective, charges and their respective valence electrons. But anyway, we learned that the driving force of chemistry with respect to chemical reactions was trying to fulfill the octet, okay, maintaining the 8 electrons around the valence electron, the outermost shell, okay. And from that, we're able to determine that these atoms that are neutral charge become ions by either gaining or losing electrons. And we learned that metals lose electrons because they have multiple reasons, but they tend to lose electrons, whereas non-metals tend to gain electrons. And in both cases, by losing or gaining electrons, you eventually fulfill that octet, okay? Then we start putting those ions together to make compounds. And we put these compounds together, and at the right ratio of atoms, we started with making ionic compounds, which is a mixture of metal and non-metal elements. And then we talked about putting compounds that are a mixture, a combination of non-metals, which resulted in the first 2 types of compounds: ionic compounds, which is a metal-non-metal combination, and covalent compounds, which is a non-metal combination, okay, giving us covalent bonding. The difference being with ionic compounds, it is more of electrostatic attraction, meaning that the ions come together just like 2 magnets coming together. The attraction is that we got a full positive charge and a full negative charge. They come together to form an electrostatic attraction and form these ionic compounds, creating ionic bonds. Now, the main part about the ionic compounds is that when we put them in water, they will dissociate. Now, some of them dissociate 100%, totally dissolve in it, and some do not. And we learned about the solubility of these compounds, of these ionic compounds. And the ones that were insoluble, classified as insoluble, even though they're insoluble, where the bulk of it's still combined, there are some ions still in solution weakly, because they would dissociate maybe less than 1 to 5%, compared to those that are defined as soluble. They're literally 100% in solution. Okay, so we made ionic compounds, and there's no sharing of electrons. We have an ionic bond. Then we learned about covalent bonds, where there is an actual sharing of bonds of electrons. And there's two types of sharing: equal sharing and unequal sharing. The equal sharing resulted in molecules that we defined as classified as nonpolar, okay? Whereas the unequal sharing, and you had unequal sharing simply because in that bond between the two nonmetals, they're dissimilar. One, it'd be like an A-B scenario, okay? And an AA scenario, meaning the elements are the same, resulted in a, wow, that was a crazy line there. Okay, resulted in a scenario where you have two elements, and I put generic elements there, AA, where they are, we're talking covalent bonds, but they're the same, meaning that their electronegativity is the same, so result in a non-polar bond, okay? Because the electronegativity, which is a measure of, and kind of bringing everything together here. So a lot of this is react. So comes all together to this intermolecular forces. And so the nonpolar bonds resulted in a nonpolar molecule, which is important to learn to identify, because once we know that something's nonpolar, we can assign to it a specific intermolecular force. Now, that will come a little bit clearer in a second. Now, when the scenario was that we have two nonmetals that are not the same, two different, carbon-nitrogen bond, we ended up with a polar bond, okay? A polar bond. Why? Because one of these, either A or B, had a higher electronegative value, resulting in that bond being unequal sharing, because the one with a higher EN value would pull the electrons onto itself much more than the other, resulting, and let's assume here that B was a lot more electronegative, so we ended up with a partial negative on the B and a partial positive on the A. We actually made a polar bond. Polar meaning that we have two poles, like the Earth, North and the South Pole, like a magnet, a North Pole and a South Pole, okay? In this case, we have a partial positive and a partial negative. We need to identify we need to learn how to identify the molecules as with respect to being polar, because once we know that, we can assign a specific type of intermolecular force, okay? And so all that we talked about before is coming down together to this in the type of bonds, okay? And what's going on with respect to these forces that then have effect on the overall property of the molecule, okay? Which then affect the whole container. And that explains why when we do a compare and contrast, which we're going to be able to, why some molecules have a higher, for example, boiling point than other molecules. Why certain things require, like water, 100 degrees temperature Celsius to get it to boil, but something like ethanol or alcohol boils somewhere around 78 degrees. Okay, both of them are polar. Both of them have polar properties. But because of these intermolecular forces, it results in a different type of boiling point. So intermolecular forces have a big effect on the properties of the overall, the macro properties of the compound. Okay. And so the polarity aspect, it comes in, we're needed again. We need to make sure we master that ability to look at a compound and determine whether it's polar or nonpolar. Okay. Now, in general rule, if you recall, when a molecule had all nonpolar bonds, okay, all nonpolar bonds, we ended up with a nonpolar molecule. Okay, which then once we know that, we can assign a specific intermolecular force. Now, we also learned that when a molecule has polar bonds, okay, in the molecule, and they do not cancel out, okay, cancel out, then we ended up with a polar molecule. Now, I'll have a few words more in a second. So remember, we defined a polar bond in a molecule because the two dissimilar atoms automatically have a polar bond, with the exception of carbon-hydrogen. If you recall, carbon-hydrogen, the electronegativity of carbon and hydrogen is essentially the same. So it is a non-polar bond. But everything else with respect to two non-metals coming together, they have a polar bond, okay? And that means that they're all polar bonds in a molecule and nobody gets canceled out. If you recall, we had that arrow, the polar arrow with the little plus in the end, okay? If we have two dipoles going in the same direction, the net is magnified. So if this had 5 units of polarity and this had 5 units of polarity, and both of those bonds are going in the same direction, so the net would be 10 units of polarity. Now, if you take and reverse one of them in a different direction, so we got 5 units going to the right and negative 5 units going to the left, guess what? They cancel each other. So it is a zero, net zero. And that's what we mean by if they don't cancel out with respect to the bonds. If they do not cancel. If they do cancel, then you have a non-polar molecule, okay? If you recall, we did an example with carbon dioxide, okay? Well, we had a dipole from the carbon to the oxygen on both directions, and they both had the same magnitude, but they're going in opposite directions, just like this scenario here. Now, regardless of the magnitude, the fact that they're both the same bond and they're going in opposite directions tells you that we ended up with the net zero polarity, which meant that carbon dioxide, even though it has polar bonds, resulted in a non-polar species, okay? Once we know that, then we can assign an IMF, okay? Once we know the polarity of the molecule, we can assign an IMF, okay? And all right, so let's discuss. So that's a rehash of the information you're going to need for this particular chapter. Kind of summarize it, kind of bring everything together, at least an attempt. So what we have here is to explain what are IMF interactions. Okay. Well, let's take a look at it. Intermolecular forces. Now, there's two types of these forces. There is an inter that we're talking about here, and then let me back it up. Okay, there's an inter versus an intra. Okay, versus intra. Now, if we just look at the prefix and just to define what what's the difference between inter versus intra, and there's a lot of ways to describe it, that term, but let's give you a couple of examples. Sports, collegiate sports. You may have heard the expression of intercollegiate sports versus intra-collegiate sports. Let's take basketball. When it's an intercollegiate sports, that means that, say, SCC would be playing a GCC or other colleges, right? Whereas intra, you might be playing basketball within little groups you have created within SCC. All right, so inter is with others, and intra is within yourself, if you will. Just like international traveling, going out to other countries. Intra would be, we're staying here in the U.S., going from state to state. Okay. Now, what is going on is with respect to inter, is I'm going to draw a molecule just as a circle, and there's an interaction that's occurring, and that's supposed to be a dotted line. There's an attraction occurring. Okay. Recall that we can have dipoles in here, in these molecules, with a positive and negative. It's like, think of it as a bunch of magnets all on your table, and they all line up, where the north attracts to the south, and so on and so forth. So this is the intermolecular force that's occurring. Okay, that is the interactions of a molecule it has with another molecule, be it itself, and even be it with something different. Okay, with respect to inter, that would be what is happening, basically bonding. What is happening within the molecule. Okay, maybe we got two species here. So we're looking at the bond between two elements. And we've talked about the type of bond. We talked about an ionic bond, or a polar covalent bond, or a non-polar covalent bond. Okay, so we have to distinguish the two. Now, these intermolecular forces are strong, but not as strong as bonding. So, but anytime you want to break up that interaction, you need to give it energy. Good example, which we're going to talk about here, but something to kind of get you ready for this, is, I imagine you can see this already. If you take a cup of honey and a cup of water, all right, and then you do a little race to see who's going to empty that cup. What do? You take them, flip them over, or the sink. Okay, who do you think is going to win that race? The water or the honey? Who's going to empty out completely? What is the true thing, based on what you know about honey and what you've seen about water? Who's going to win that race? The cup of honey or the cup of water, as far as emptying its container? If we flip them over, who do you think? Any ideas? Yeah, the water, of course. The water will win the race. And we're going to keep it all at the same room temperature, because honey is very thick and viscous, right? All right. And so, try this at home. You try it at home, and just flip over a cup of, or half, don't waste so much honey, but a little bit of honey and a little bit of water, same volume, and then see who wins that race. The water, no problem, Debbie. The water is going to win the race. Now, why is that? That is because the intermolecular forces, are stronger for the honey than for the water, resulting in giving a specific type of property, what we call viscosity, making it thicker, because of this force that's occurring in here. Now, take that same race. Now, how can I make that honey flow a little quicker without diluting it? What could I do to that honey? to make it flow as quick as water? What do you think? You heat it, of course, right? Common sense that I'm going to heat it. Well, guess what you're doing? When you heat something, you make it go flow quick more. You are breaking up this force in here, that attraction that the molecules have for each other. So that interaction now is not as great as it was. And therefore now the flow is quicker, could be just as fast as water is, okay? So energy causes the breakup of those forces that changes the properties. All right, so intra versus inter molecular forces. So in this example here, we have two molecules, looks like a diatomic molecule, okay? And a lot better drawing than I did. So what we're dealing with right here is denoted by the dotted line are the intermolecular forces between the molecules. And what's called the intra is what is happening within the molecule, basically what type of bond it is, okay? Now, the forces are not bonds, they're attractions to each other because of the differential with respect to the dipole in there. A lot of these molecules have a permanent dipole. There's a permanent partial positive and a partial negative. Some of them do not. Some of them actually have what we call a temporary induced dipole. We'll have more on that here in a second. All right, so clear my mess here. Okay, so we're not, these forces, I was going to say, they're not as strong as bonds. We're not breaking bonds. Bond energy takes a lot of energy to break a bond. Here, we're just talking about forces that are strong, but definitely not as strong as an actual bond. So we're not breaking any bonds here, okay? We're just breaking up the attraction. Yeah, think of it in terms of, I've worked with some very strong rare earth magnets. Now, you know there's refrigerator magnets, and you put them together, they're very weak. They attract each other, but you can very readily pull them apart. And then there's a little bit stronger magnets that takes a little bit of oomph because you got to break it apart. And then you got rare earth magnets that are extremely strong. I did work with these in my career. And if you ever get them to snap together, they can literally pinch your skin and take out a chunk of your skin. And to pull them apart, a lot of energy requirement. And so think of that as the intermolecular forces. And there's going to be different strengths, just like these different magnets we just talked about. So obviously the ones in the very rare earth magnets are going to take a lot of energy to break apart compared to refrigerator magnets that wouldn't take that much energy to break apart. Okay, so in this example, we're talking about hydrochloric acid, or HCl, hydrogen chloride. Okay, let me change the color a little bit. Okay, so here we got the intermolecular force. Now, the reason we have that interaction is because what? We have a dipole. Okay, we know that there's a dipole here between hydrogen and chloride. There is a partial negative on the chloride and a partial positive on the hydrogen. Well, with respect to another molecule of that, HCl, similar scenario. So you can see where the positive and the negative will be attracted to each other. There will be an attraction there. Okay. Now here we draw it one dimensionally, but think of this, we live in a three-dimensional world. So here's this picture, just one dimension, but these molecules are all around. So it kind of, though they're moving around, it does give them a little bit of in the liquid phase, it is a little bit of a structure to it because of the dipole interactions here, because of the intermolecular forces. Okay. All right, now there are four types of intermolecular forces. Now, how we assign these is learning how to refresh your memory and how we talked about in the beginning about defining a molecule as to if it's polar or non-polar, and then recognizing that you're dealing with ionic compounds. Now, if you deal with ionic compounds, you're going to be dealing 99.9% of the time with ionic compounds in an aqueous solution. Okay, aqueous solution. All right. The first type is called a London dispersion force. Okay. London dispersion forces are probably the weakest force. And we'll come back to that in a second. Then we have what's called a dipole-dipole force. So we'll give you some examples here, specific examples in a second. A dipole-dipole, just by the name, you can think about it like the HCl example. We have a dipole hydrochloric acid interacting with another dipole molecule of HCl, okay? So that would be a dipole-dipole example, okay? Then we have a special type of it is a dipole-dipole, but because of the nature of the beast, so to speak, it's very specific. It deals with hydrogen that is bonded specifically to nitrogen, oxygen, or fluoride, okay? Though there is a dipole, that interaction results in a much stronger force involved. So between these three, London dispersion forces is the weakest. The strongest interaction is number three, hydrogen braking force, and then dipole-dipole is somewhere in the middle, okay, with respect to strength. And that's important to know, because if we get two molecules and we determine their polarity of the molecules, from that polarity, we can assign one of these forces. Once we assign one of these forces, we can do predictions to do a relative comparison of a physical property of, let's say, boiling point. We can't do absolute values. We can't say this molecule will have an absolute boiling point of X because of this force. No, we can't do that. But what we can do is say molecule A versus molecule B will have a higher boiling point because it has this type of intermolecular force compared to B, which is a stronger force for that in B, therefore we have a higher boiling point, okay? And we'll get into specifics. And then the fourth one, they call it ion dipole force. Now, the key word here is ion. So ion should direct you to, I'm dealing with an ionic compound, okay? And specifically, when they talk about a dipole force, we're dealing with an ionic compound, which, like I just stated, the only thing an ionic compound can really solvent-wise it can interact with is an aqueous system. I stated earlier that because of solubility rules, some ionic compounds totally interact with water and totally dissolve, whereas other ones, depending, that are labeled as insoluble, don't interact as extensively as those that are classified as soluble. But there is a small amount of it that does interact. The point being, when you see ion dipole forces, think ionic compound in aqueous systems, okay? Ionic compounds in aqueous systems. So with respect to the type of compound, covalent compounds are for 1, 2, and 3, whereas we're dealing with ionic compounds for number 4, okay? All right. Now, with respect to London dispersion forces, any molecule that is classified overall as nonpolar and P, automatically the only force they have to deal with is London dispersion forces, which, by the way, are the weakest forces of these three, okay? Now, in number 2 is a dipole-dipole, which means that the molecules, for example, have to be polar. Okay, that's a requirement. To be polar, they have a dipole, permanent dipole, like the example of HCl, the one we saw earlier, where you had HCl interacting with another molecule of HCl. That is an example of a dipole dispersion force, okay, or dipole force. Now, number 3 also has to be polar. Okay. It also involves a dipole. However, it involves specifically hydrogen that is bonded to either nitrogen or oxygen or fluoride. Okay. So it's hydrogen on NOF or not on file to help you out. So it is a dipole, but it's a very special dipole. It has an additional attribute, so much so that it's given its own name, hence hydrogen bridging force. You may also see literature someplace out there, they call it hydrogen bonding. AKA, also known as hydrogen bonding. We're trying to stay away from the term bonding. Hence, the word bridging is the newest, not newest, but the up-to-date naming, because bonding gives it an impression there's an actual bond involved, and there really isn't. There's no sharing of electrons. It's an interaction, okay? Just like ionic bonds, it's not a true bond per se, as we think of bonds and where you got sharing of electrons. Ionic bonds is more of an attraction. So I see the day when even that can be, that name will probably be changed. So you may see it as hydrogen bonding, but the correct term being used is hydrogen bridging force, okay? And then you have the ionic dipole force. Well, like I stated, it's got to be an ionic compound and associated with an aqueous system. So it could be like sodium chloride in water, would be an example, or any ionic compound in an aqueous system. All right, so you can see here that we have to assign a specific force with respect to covalent compounds. We have to determine its polarity, okay? And to determine the polarity, sometimes we may need to use, remember the Lewis dot structures way back when, okay? Because the Lewis dot structures will give us a better picture of the geometry, and check to see if, in fact, polar bonds don't cancel out, okay? Because, like I stated earlier, you can have a scenario where you have polar bonds, but because in their position they cancel out, you end up with a nonpolar species. Okay. Refresh your memory, we did the carbon dioxide example, but we also did the tetrahedral, where we had carbon tetrachloride. Okay, so C, carbon, and 4 chlorides are on. It could be any halogen, but carbon tetrachloride. You can see here that we have 4 polar bonds, but because of the geometry of it, all four polar bonds cancel out, resulting in a nonpolar species, okay? Carbon dioxide was another one that because of the geometry, which is linear, the polar bonds were opposite of each other, and they canceled each other out. If you have to do a Lewis dot structure, remember as a general guideline, when you end up with a lone pair on the central atom, like ammonia is a good example, but it's got lone pair in the central atom, automatically think polar molecule, okay? You can have 1 lone pair or at the maximum 2 lone pair, like water. H2O has 2 lone pair. Water is extremely polar, most polar solvent that exists. Okay, so those are the forces. And we'll go on and talk a little bit more about it. All right, so here's the thing about London dispersion forces. First of all, they're temporary. Okay, I just mentioned that the force here is associated with nonpolar molecules. Nonpolar molecules. Now, what happens is, even though they are nonpolar, they can still form a temporary dipole. And I'll give you a specific example. I'm sure you've seen or maybe done it yourself where you get a balloon, okay, and you rub it on your head or someone else's head, whichever. So what is happening there is as you do that, recall that electrons are all around us, okay? I mean, it's why you wake up maybe with a bad hair day. Your hair is like poof, right? You say it's the environment, but you have a static hair, or you have clothing that clings onto you, or you walk on the carpet and you touch metal and you go spark. Well, those are electrons, and they're all around us, all around our body, all around us. Well, if you take that balloon and you rub it in your head, okay, you in effect are transferring some of those electrons that are on the surface of your hair onto the surface of the balloon. Okay, so now that balloon, okay, here, this represents my balloon. That balloon now has electrons all over the surface, right? Electrons with a negative charge. So there's a high negative density around the balloon. So as you bring it to your chest and let it sit there, it clings, it sticks, right? You want to think about it for a second. As I stated earlier, on the surface of your chest, your shirt, whatever, there's electrons. Why would it stick? Because you got negative and negative. Well, what's happening is those electrons in the balloon are repelling the electrons on your chest and moving away from the surface someplace else, resulting in a more positive character on your chest. More positive, like a partial positive, then can interact with the partial negative of the balloon. And guess what? They hold on. Okay. That balloon sticks there. And you know you can't walk with that thing all day because it's only temporary. With time, that thing just falls off. Okay. Because the electrons eventually dissipate and do other things. Okay. So those are and what is happening with nonpolar molecules and why there's an attraction with them. Now, note about this. As the nonpolar molecule gets bigger, if I want to compare and contrast two nonpolar molecules, the bigger one would have more London dispersion forces than the little one, simply because there's more surface area, more on the larger molecule than the smaller one, okay? So its force, though both being London, both being weak, but one will have greater forces. And that is why certain fatty acids are a good example. Fatty acids, they have a polar end, but they have a non-polar end. Okay. And a non-polar end, that's what we call them fatty acids. The acid part is the polar end. The non-polar end is are basically hydrocarbons. Some hydrocarbons, you know, there's like vegetable oil, which is a liquid. Okay. But then you also have vegetable, I'm trying to think of the name, it's like lard. It's solid. Well, not like a rock, but a lot more solid than the liquid. And that's because there are more London dispersion forces in the lard, if you will, than in the liquid. Some other factors involved, but that's one of the reasons. All right, so as stated here, bigger molecules, obviously more electrons, more surface area, more London forces, okay? And this here kind of depicts what I just was telling you using the example of the balloon, where you're getting two nonpolar molecules. They're basically coming together, and the electron density on one side is forcing, the electron density of the other side to go away from it because they're repelling. So in effect, we are creating a partial negative and a partial positive, and hence we have an intermolecular force, which we call London dispersion forces. Which of the three is the weakest? Okay, is the weakest. All right, so with respect to dipole-dipole forces, in this case, we have a permanent dipole. The dipole we just described here is a temporary dipole, the partial positive side and the partial negative. But with respect to polar molecules, the fact that we have two dissimilar atoms bonded together, we automatically have a permanent dipole, okay? And we have a permanent partial negative side and a partial positive side, with this example being HCl. Okay, here is our interaction. Oh, where'd it go? Our interaction right here, our force right here. Okay, the partial positive is attracted to the partial negative being attracted to the partial positive of another molecule of HCl. We are not talking about the bond itself. That would be intra, and that would be a polar covalent bond. That's the force that is holding the hydrogen and chloride together, okay? With respect to this one, where we have dipole-dipole force, okay, that is the force that is holding HCl molecules together. Note the difference here. Holding the molecules together is dipole-dipole force. Holding the specific atoms together is in the polar covalent bond is the is a polar covalent bond. Okay, that's the intra. I write that wrong. INTRA versus INTER right here. Okay. All right, so I stated earlier, with respect to strength, and when we talk about strength, is basically, well, how much energy would it take to break that interaction apart? That's what we're talking about. And so the dipole-dipole forces will require a little more energy than the London dispersion forces. So they tend to be a little bit stronger. The interaction is a little bit stronger. All right, so note, remember HCl here, and we'll come back here for the other one. Hydrogen bridging force, okay? This is an especially strong dipole force, and it's much stronger than the dipole-dipole that it has its own name. Hence, it's called hydrogen bridging force. And it involves, as I stated earlier, a hydrogen. You must have a hydrogen that is bonded either to a fluoride or an oxygen or a nitrogen. Okay, here's the NOF, 905. Okay. Note what we just showed earlier with HCl. We have a hydrogen, but it's not bonded to nitrogen, oxygen, or fluoride. It's bonded to chloride. Okay, and so this would be dipole-dipole force. But if we had a hydrogen fluoride example here with another hydrogen fluoride, that interaction would be called the hydrogen bridging force. Note the difference, okay? Or that could have been nitrogen, or that could have been oxygen. Okay. And like I stated, it's very strong. Water has a lot of hydrogen bridging force. And here we think of the model as three-dimensional again, because you have these interactions going all the way around. And those forces can be pretty hefty enough that if to boil water, you need to get up to 100 degrees temperature to get water to be converted from liquid to the vapor phase, because what you're doing is you are breaking up all these interactions with that energy. As you heat water, you're forcing these molecules, you're putting kinetic energy into the molecules, which is causing them to move around quicker, eventually to move around so quick that they pull away from each other and go into the vapor phase. Okay. Excuse my dog in the background. We got a new puppy and he's learning. Right, puppy. He's 10 months old and he's big as a horse. He's a mix of, I don't know, white Shetland pony, I think. All right. Hydrogen braking forces stronger than dipoles and much stronger than London forces. Okay, but we're still not talking about the strength of either an ionic or a covalent bond. Right. Now, with respect to the ion, the fourth one, okay, the name is ion dipole force. Now, the key word, as I stated, or this prefix or word is ion. We are dealing with ionic compounds, okay? And we're dealing with a dipole, specifically hydrogen bonding force, but that's, we just call it a dipole force right now, because we have sodium interacting with the water molecules all around it, okay? And it's sodium in this example, but it could be any metal ion, any metal ion. And then you can see the water molecules are totally solvating the sodium ion, but then let's say if this was sodium chloride, then the chloride could be over here interacting with the positive side because the chloride has a negative charge, okay? The anion of the sodium will be interacting with the hydrogens of water, and very strong interaction, okay? So again, for it to be an ion dipole force, you have to be dealing with an ionic compound and an aqueous system, okay? All right, excuse me. So let's kind of summarize the differences between the two here, okay? You know, I mentioned earlier we're talking about inter versus intra. Okay, this is the inter forces versus the intra forces. Okay. And the bonds are obviously ionic bonds are the metal non-metal interaction, the electrostatic interaction that keeps the ions together. The covalent bonds, be it polar or non-polar, these electrons are actually shared, which either going to be shared equally or not equally, okay, resulting in either a polar covalent bond or a non-polar covalent bond. With respect to the forces, all non-polar molecules, okay, all non-polar molecules, the only force they have are the London dispersion forces. The requirement to have the dipole force is one, they got to be a polar molecule, and hence we're dealing with covalent compounds, right? Covalent compounds, in fact, all of them here. The first three are covalent compounds. Whereas here, we're dealing with ionic compounds in water, aqueous system. And hydrogen braking force, that is a hydrogen bonded to either a nitrogen, oxygen, or a fluoride, all right? Which is, of the three, the strongest, has the strongest force, which therefore will require the strongest amount of energy to break it apart. Okay. All right. And then the ion dipole forces dealing with ionic compounds in the aqueous system. So that kind of distinguishes the two, and questions are asked And in order to decipher what the question is asking, you really have to read the question carefully and ask yourself when you read the question, are they talking about the interaction of molecules with each other, or are they talking about what is holding the atoms together? Are they talking about bonds? Okay. Are they talking, is the question asking about the specific bond, type of bond, or is it asking about the force that molecules of whatever compound, what force they have intermolecularly, if you will? So we have a table of compounds, and we're asked to determine the strongest type of IMF, intermolecular force, in the samples of these molecules. Okay, and so we're given CO2, PF3, HF, and CHF. Okay. And then you have potassium iodide, and they say aqueous. So that right there should tell you it's not the London dispersion forces. It's not a dipole-dipole. It is not hydrogen bridging force. It's the ion dipole force for Ki, because it is an ionic compound in an aqueous system. All right, so we'll get to that in a second. So we look at carbon dioxide. We first have to determine whether it is polar or nonpolar. And so if you don't know what it is, we use the Lewis dot structure. And we came up with that. And then we noticed that, yes, it has two polar bonds, but they go in opposite direction and they cancel each other. The result is that carbon dioxide is nonpolar. Okay, though it has polar bonds, but they cancel out, therefore it's nonpolar. Therefore, automatically, the only force you got to deal with is London dispersion forces. Okay. PF3. Again, you may not know what it is structurally, but you know, we will always tell you who the central atom is. But by default, 99% of the time, the first atom written in the formula is the central atom. Okay, so if you do the Lewis dot structure, you will come up with the following structure. And then I'm not going to put all the electrons around the fluorides, but there's a bunch of them. There's 8 around the fluorides. So, but eventually, guess what? You end up with a lone pair on the central atom, which, as I told you before, whenever you end up with a lone pair in the central atom, guess what? We have a, what's going on here? We have a polar compound, okay? Now that we know it's polar, we can eliminate London dispersion forces, right? Because London dispersion forces, we can eliminate that. Okay, London, because London only deals with nonpolar. So we can eliminate the ion dipole. Eliminate that because there's no mention here of ions, specifically ionic compounds. Okay, so what we have left is dipole-dipole force or hydrogen bridging force. Okay, we can eliminate the HBF. Why? Because there's no hydrogen involved here. So we eliminated that. So the only force you have to deal with is dipole-dipole force. That's it. So again, systematic approach. We went through, figure out what the structure is. From the structure, determine the polarity, unless you knew what the polarity was to begin with. From the polarity, you can eliminate, 2 of those forces. We eliminated 2 of the forces, leaving us with 2 other forces. And again, by process of elimination, we bring it down to what the only force it can be. Okay. So when you have a polar molecule, polar covalent compound, the vast majority of the compounds are going to be a dipole-dipole force, okay? Because in order to have HBF, you got to have hydrogen with nitrogen or oxygen or fluoride, okay? And so like, probably 99% of the molecules would be DDF, hydrogen bridging force. Let me clear my mess here. All right, which brings us to which brings us to HF. All right, hydrofluoric acid or hydrogen fluoride here. Two molecules, so it's not, obviously it's not diatomic because you got a hydrogen and a fluoride. So automatically you got a dipole, okay? But on top of that, you have hydrogen, which is bonded to fluoride. So we know automatically it's polar, okay? Because two dissimilar atoms are bonded together. And it's linear, so there's no way they can cancel each other out. So then from that, it's either going to be dipole-dipole or hydrogen bridging. Well, it can't be, I shouldn't say can't be. It has to be hydrogen bridging force. Why? Because we have hydrogen bonded to fluoride. So that's the force. Yes, it is a dipole. And if you label it dipole-dipole, unfortunately, you're going to be kind of wrong because it's a special type of dipole-dipole. It's a little bit stronger than a dipole-dipole. Okay. All right. Carbon, hydrogen, fluoride. Automatically, all you see is carbon, hydrogen, hydrocarbon, think nonpolar. You don't have to go any further. The only force you can give it is London dispersion forces, okay? Because it is a nonpolar species. And then the Ki, you got a, it's not either polar or nonpolar, because what you have is an ionic compound in a polar solution, okay, which is water. And so what you have here is an ion dipole force. Okay, now with respect to compare and contrast, we can only do that for the covalent compounds. Okay, these. Now, if I needed to do a compare and contrast, and I was asked a question, of these four molecules, okay, 1, 2, 3, and 4. If I was asked the question, who has the higher boiling point, okay, I would say of these choices, hydrogen fluoride would have the highest boiling point. Why is that? Because it has the strongest force, intermolecular force. Having stronger intermolecular force, it requires more energy to break up that force to cause the molecules to go from the liquid phase into the gas phase. And the contrast of that, if I'm asked, well, who would have the lowest boiling point? Boiling point is that temperature where a liquid goes to a gas molecule. So in this scenario, the ones with the lowest boiling point would be the ones with the London dispersion forces, okay, which are the weakest, okay? And case in point here, both carbon dioxide and CH4, which is methane, are gases. Because at room temperature, they go automatically into the gas phase with not a lot of energy. It takes a lot of to bring it down to liquid phases. You got to go way below zero, way below zero. And once you heat it up just a tad, those things should go automatically into the gas phase, okay? Because the forces are extremely weak. Okay, and then PF3 will be somewhere in the middle. again, we're not doing absolutes. We're just, saying we can do a relative comparison. And I keep mentioning boiling point, but there are three other physical properties that we're going to look at. One is called vapor pressure, surface tension, and viscosity. Okay. And all of those are related to those properties are related to the intermolecular forces, which, by the way, is related to the electrons around the molecules. It all comes back to these crazy electrons. All right, let's clear the table here. All right. Now, we have a little law here that kind of help us with the charge. We're not going to make you responsible for the for the equation which is written here, but what we're trying to say is this: Coulomb's law is just an equation to measure a force between two charged particles. Okay, and this electrostatic attraction between the attraction between two particles, two charged particles, be it atoms or be it dipole molecules. But it's proportional to the magnitude of the charge. Proportional meaning that the force of this interaction will go up as I increase the force. So when it's proportional, I increase one variable, the other variable goes up proportionally. Okay. But it's inversely proportional to the distance between the two charges squared. So inversely means that if I increase one variable, the other variable will go down. But this one goes down even more dramatically. It goes down by the factor of the square, the value to the square value. Okay. And that's Coulomb's law. F is the force. Now, what I want to do to demonstrate what all this means is that I'm going to take these variables, the K. Oh, let me change the color here. I'm going to take the K and the Q, and I'm going to combine them. Okay. And I'm going to hold them constant for mathematical purposes and just redefine them as a new variable, which I can do that. And I'll just say F, the force, is equal to some value X divided by R squared. I'm keeping R squared. R is the radius, the distance between the two charges. Okay. Now, scenario number one. Let's say, number one, that R is equal to 1 unit. Okay, we don't have to be concerned about the absolute unit, it's a unit. Okay, and so what this means is that the force is equal to X divided by 1 square, right? Which 1 square is 1 times 1 is 1. So the force is simply equal to X, whatever X may be. Okay. I could, to make it even more dramatic, let's call X. Let's define X as a specific number. Let's just say X is equal to 100. Okay. So to see how this really works mathematically. And so we go F is equal to 100 divided by R squared. So R squared is 1. That means that the force is equal to 100, right? Right, so that's our force. Now, scenario number 2. Let's take R, and there's 2 molecules, charges that are at 1 unit apart, and now we're going to double the distance between them to go to 2 units. We're doubling from 1 to 2 units, okay? So in that scenario, F is equal to 100 divided by 2 square, okay? Which is 100 divided by 4, right? Which is equal to 25. So for scenario number 2, when we double the distance between those two charges, the force between them decreased by a factor of a fourth, 25%. The value now dropped to 25. Okay. Now let's do the opposite direction. Where R start off as 1, let's cut that distance by 0.5. Okay. And so now let me go over here. The force is equal to 100 divided by 0.5 square, which is 100 divided by 0.25. Check my math, and you will see that to be 400. Check my math. 100 divided by by 1/4 is 100 times 4, which is 400. And so in scenario number 3, when we went from a 1 and dropped it down to half the distance, that force, that interaction between those two charges went up from 100 to 400. It increased by a factor of 4. Okay. And very dramatic as far as the force, because it's inversely proportional to the distance between them squared. And the best analogy I can tell you is this: if you could take two magnets and you put, let's say, the opposite charges or two souths together, and then just bring them together, you can feel that repulsion and just keep them there for a little bit where they're being repelled, but not very strongly. Obviously, if I double that distance away, that force, though it's still there, is very, very, very subtle. Okay. But if I go back to where I was and then I decrease that by half, you can feel that repulsion force really strong. Okay. And that's what's happening here. And that is demonstrated mathematically by Coulomb's law. And just to say that the force of the interaction between the two charges is proportional to the charges. So if the charges were 1 and 1, okay, then you have 1 times 1 is 1. But let's say the charge was 1, the other one was 4, right? You've increased that interaction by a factor of 4. But then the force is inversely proportional to the square of the distance between the radius. Okay? And it drastically decreasing the distance between them drastically increases the force. All right, so that kind of shows it mathematically and shows you how dramatic that is as far as that equation is concerned. All right, let's do this. Let's take a quick 15-minute break. I got 2:50. Let's come back at 3:05, and we'll finish this up. 3:05. Okay. All right. We shall return. Let me pause the recording. Okay, I'm back. All right. What we have here is a series of questions where they're asking you to either determine if what type of force. Basically, is it an intramolecular force, which is the type of bond, or if it is an intermolecular force. And to determine that, remember, we have to determine, well, is that molecule polar or nonpolar? And then from there, determine which of the 3 or 4 forces we're going to assign it to. All right, so we have to read the questions carefully. Okay, for example, the first one. What holds the atoms together in one ammonia molecule? Okay. And so the thing to ask yourself first, are we talking in Inter versus intra. Okay. What do you guys think? Is that question, is that an inter or intra question? Check out the keywords in a sentence in which I've underlined. What is holding the atoms together in one ammonia molecule? What do you think? Anybody want to give it a shot? Okay. Well, I guess I'll take it. It's an intra because they're asking you for one ammonia molecule. Okay. They're not asking about how one ammonia interacts with others. And so then we have to determine, well, what type of bond that is. And that's a bond between nitrogen and hydrogen, which is a polar bond. Okay. Specifically a polar covalent bond. All right, next one is asking, what is holding the sodium ions in water? Okay, so here we have a binary system. We have the sodium ions, which is an ionic compound, and water, which is an aqueous. So what are we talking about here? Are we talking about intra or inter? What do you think? No? Okay, well, we're dealing with two species, the sodium ions in water. Okay, so that would be definitely an inter relationship. And specifically, that would be the ion dipole relationship. Okay, the ion dipole. Now, here, the next one says, what is holding three HCl molecules together? All right, and so keyword three HCl molecules. So definitely it's got to be interaction. Okay. And so next step is determine, all right, what HCl? Is it nonpolar or polar? Well, obviously two dissimilar atoms, H, hydrogen, and chloride, tells you it's polar. All right. So we can eliminate both the ion dipole and the London dispersion forces, right? Because we're dealing with a polar species. So all we got left is dipole or hydrogen bridging. You might be tempted to do hydrogen bridging simply because we got hydrogen there. But remember, hydrogen bridging only applies to hydrogen bonded to nitrogen, oxygen, and fluoride, of which chloride is not. Therefore, the type of intermolecular force here would be dipole-dipole forces. All right, so here, the question is, what is holding the ions together in salt? Okay, so in salt, there's no mention about an aqueous system. They didn't say a salt solution, right? They just said in salt. So we're talking about solid salt, all right? So next thing is, all right, we're dealing with salt, sodium chloride. Well, what type of bond are we dealing with? It's obviously an ionic bond because we got a metal and a non-metal. And so we have ionic bonds, and that is what is holding the ions together in sodium chloride. What is holding four H2O molecules together? Again, we're dealing with four molecules of water, so that would infer that it is an interrelationship, okay? And so then we need to find out, okay, what kind of molecule we're dealing with. We got H2O, extremely polar solvent, no questions about it. So we can eliminate London dispersion forces and ion dipole forces. So we're left with dipole-dipole or hydrogen bridging. We have hydrogen that is bonded to oxygen. Therefore, the only thing that could be is hydrogen bridging forces. That is what is holding four H2O molecules together. Next question. What holds nitrogen gas molecules to each other? Okay, to each other is the question. And so what would that suggest with the keyword to each other? Would that suggest an inter factor or an intra relationship? What do you guys think? Which one for nitrogen molecules? What holds the nitrogen gas molecules to each other? What do you guys think? Any ideas? What do we got? Okay, inter. That would be correct because the key word is each other. All right, so we're dealing with the interrelationship. So now we got to find out, all right, so is it polar or non-polar? Is nitrogen polar or non-polar? Would be the next question. Right, so that's what we need to determine before we can go further. Is nitrogen polar or non-polar? Keep it in mind that it's two nitrogen atoms, the diatomic is two nitrogen atoms bonded together. Okay. And having two atoms that are the same represents two electronegativities that are the same. Therefore, you have equal sharing. Therefore, you have a nonpolar species. And having a nonpolar species for oxygen molecules, remember all the diatomics are nonpolar. That being the case, being nonpolar automatically sends you to London forces, okay? And that is true for all diatomic molecules and for all hydrocarbons, the carbon-hydrogen bond, okay? Or anything that is nonpolar, okay? Any nonpolar molecule, carbon, hydrogen, hydrocarbon, or diatomics, all of them are nonpolar and therefore London forces. All right, next one. What is holding the oxygens together in an oxygen gas molecule? All right, so we're talking specifically about one molecule. So definitely not an inter, but an intra. So the question is, it's a covalent bond, okay, two oxygens together. More specifically, it is a nonpolar covalent bond, okay? And then finally at the end is what is holding two ammonia molecules together? So we're talking about an interrelationship because we're talking about two ammonia molecules together. And second of all, once we determine that, is it polar or non-polar? Well, ammonia definitely polar, okay? So that means either hydrogen bridging or dipole-dipole force. Well, since we have hydrogen bonded to nitrogen, which is the criteria for hydrogen bridging force, that is the only choice it has, and it's hydrogen bridging forces. Okay. All right, so that's what we do with these type of questions. Okay, excuse me for 1 second. I got to sneeze. Excuse me, something just made me want to sneeze real bad. All right, so how to answer these questions is one, systematic approach. One, determine from the question, are we dealing with inter or intra relationship? What is the force we're dealing with? And you read the question and they're talking about one molecule, they're asking intra. So therefore, what type of bond does it have? if we're dealing with interrelationship, because we're talking about more than one molecule and how it interacts with how they interact with each other, that's definitely an interrelationship. And we have to determine its polarity. From the polarity, we can then assign it one of the four forces. Okay. All right. Bear with me for 1 second. Okay, I'm back. And sneezing has got a hold of me. All right, so in the flow chart, my diagram didn't come out very well here, but basically, what we deal with is with IMF interactions. You know, we're dealing with covalent bonds. Even though down here, this is ionic, this is an ionic in a covalent solvent, you know, so it's an ionic water scenario. But once we determine it's covalent, if it's nonpolar, then London forces, that's all the force it has, okay? If it's polar, and so we're dealing with an ion in a water solution, then that's the type of force we're dealing with, okay? Now, if that's not the case, it could be either a dipole, but keep in mind, or it could be a hydrogen bridging. Hydrogen bridging is only for those examples where you have hydrogen bonded to oxygen, nitrogen, or fluoride. Only 3 types of compounds, and then that means everything else is a dipole, okay? All right, so once we know that, we assign what force it has, then we know that the weakest is London dispersion forces, the strongest is hydrogen bridging forces, and then dipole somewhere in the middle, okay, with respect to strength. Once we assign that to a particular molecule and what force it has, then we can do a compare and contrast, okay? Compare and contrast, which is the ultimate goal of what we're trying to do here. Okay. So, but before we do that, let's talk about these intermolecular forces and how they affect these physical properties. Specifically, we're going to talk about vapor pressure. Okay. Boiling point, I've used that as an example quite a bit, which also could be melting point. That is the temperature a solid goes to a liquid. Boiling point is that temperature that a liquid goes to a vapor, okay? And then we talk about surface tension. I have some examples of that. And then I also briefly mentioned viscosity. All of these 4 properties are affected by the intermolecular force of the molecule, okay? And with that being the case, we can do a compare and contrast between 2 molecules. All right, so what are we talking about when we mention vapor pressure? Okay, now in a closed container, we have molecules that are in the liquid, and it's a liquid in the container, but on top of the free space there, we have some of the liquid molecules that have gone into the vapor phase. So if we had a container, let's say like Erlenmeyer flask, which was something, you know, some kind of shape like this. And we capped it. And we got a liquid in here, okay? Now on the side arm, we put what's called a pressure meter. Okay? Now the liquid, denoted here by the little round dots, a chemical, whatever it may be, is in the liquid phase. Now, what's going to happen? Some of these are going to go into the gas phase. Okay. case in point, soda pop. Take your soda pop, right? If you open it up, you're going to hear a little little swish sound, right? That's that carbon dioxide that's evaporating from that upper atmosphere, if you will. And that's the vapor pressure. Now, the more atoms that are in the vapor phase, the higher the pressure. Okay. Like case in point, you have a flat tire, you're running, say, 30 psi, you got to go to 35. What do? You go to Quick Trip, Circle K, go to the air pressure air meter, pump in some more air. By putting more atoms of air in your tire, pressure goes up. Okay. So if there are more vapor phase molecules, that pressure will go up. Now think about these intermolecular forces. These are the forces that hold the molecules together as they are in the liquid phase. If they're very strong forces, they're going to be less likely to release some of those molecules into the vapor phase. Okay. So you can see, for example, hopefully, that a compound with a strong hydrogen bridging force would allow less molecules to go into the gas phase and therefore have a lower vapor pressure as compared to a liquid that has this nonpolar and only has London dispersion forces, and they're hold on to the molecules to each other much less strength. More of them are in the gas phase. I'll give an example here in a bit. Okay, so that's what we're talking about, vapor phase, vapor pressure. Okay. All right, so if we have a strong IMF, we are going to get a lower vapor pressure, okay? Because there's going to want to be more liquid, more of those molecules will want to stay in the liquid phase than in the vapor phase because they're being held down tighter, stronger than those compounds that have a weaker intermolecular force. Case in point here, you have a diagram, and by looking at the diagram, obviously you can see that molecule A, compound A, has more molecules in the gas phase. Okay, there's more of them up here in the gas phase than B. Okay, and they're all in the liquid phase, they're all together, but one of these in the liquid phase, those forces are a little bit weaker. It looks like A is a little bit weaker compared to B. Why can we say that? Because there are more of the molecules in the gas phase for A than there are for B, which would suggest that A has the weaker intermolecular force. They have the higher vapor pressure, which infers that they have the weaker intermolecular force compared to B. And because of that, they have more molecules in the gas phase. Their vapor pressure is higher. Okay. I mean, you can even think about it. I'm sure you have an example of you use an example of or have been subjected to nail polish remover. Nail polish remover is very volatile. Okay, you open the cap and then you immediately smell it's called acetone plus some other chemicals, but very volatile. A lot of the scents that are out there are very volatile, so they go out to the atmosphere. But then there's other things that don't go out to the atmosphere as readily because their intermolecular forces are stronger, like A here, and therefore less of those molecules go into the gas phase. All right, let me see. Clear this up here. Now, with respect to the boiling point, a stronger IMF would result in a higher boiling point. Okay. For example, acetone or nail polish remover, one of very volatile. It doesn't take a lot of energy to get those liquids into the gas phase. I can just rub that container with my hand. I can cause more of vapor and more of that liquid to go into the gas phase, right? But water, not so much. Okay, water requires, you need to go up to 100 degrees Celsius to get water to boil, because those forces that hold the water molecules together are very, very strong. Okay, surface tension, that's how they hold on to each other, and why certain liquids make drops or beads when you put them on the surface. So the question is, stronger IMF would result in higher surface tension. For example, like A versus B. You can see that A beat up much more than B. The molecules of A are holding on to each other much greater than the ones in B. And so the surface, A has a higher IMF than B, okay? Because they're holding on to each other much, much greater. Viscosity, like I mentioned earlier about the honey and water, viscosity is a measure of the resistance of a liquid to flow. Okay, so we know that oil, thick oil, it flows slowly, just like honey. Whereas like an alcohol, here in this example of vodka, mostly very aqueous, if it's a mixture equal with water, it's very low viscosity and it flows readily, okay? And so the stronger the IMF, the higher the viscosity. Because again, the molecules are being held onto each other much greater. And so it hinders the flow and is slow with respect to viscosity. Okay. So let's do a compare and contrast. Okay. Here, we're asked to compare ammonia with fluorine. All right. So, well, to do that, we first have to write the structure. And we have, if you haven't memorized this one, I think you should. Ammonia has the following formula, NH3. We use ammonia quite a bit. And then fluorine is diatomic. Okay. Well, diatomic right away tells you we got a non-polar species automatically, right? Which results in London dispersion forces. So we took care of fluorine right off the bat because it's non-polar. First of all, here, there's no mention of any ions, so we can not even deal with ion dipole forces here. We can eliminate that because there's no mention here. We're just talking about ammonia and fluorine. Now, you may not know the polarity of it, but you can see that ammonia is polar because it's got 3 polar bonds. Then on top of that, we do the Lewis dot structure. We end up with a lone pair on the central atom, which tells you we got a polar compound, okay? Then, with that being the case, the question is, do we have dipole force or hydrogen bridging force is the question, right? Obviously, it's not London dispersion forces because it's polar, and it's not ion dipole because there's no mention of ion here. The fact that we got nitrogen bonded to hydrogen tells us it's hydrogen bridging force, not dipole force. And so we're given the formulas, we're given the names, we have to come up with the formulas. From that, we determine their polarity, okay? From the polarity, then we assign a intermolecular force, and now we can do compare and contrast. Okay, keep it in mind that HBF has is a stronger force than London dispersion forces. Right. So we write the formulas, and then we, like we did, we just assign the force. Okay. Yep, their corresponding force. All right. So with that, now we can answer some questions. Questions number one. Which has the stronger IMF? Well, obviously the hydrogen bridging force, as I mentioned, which belongs to ammonia, has the higher, stronger IMF. Okay. Which has the lower boiling point? So the one with the lower boiling point would have the weakest force. Okay. And so that would mean that fluorine would have the lower boiling point compared to ammonia. And notice here, we're doing relative compare and contrast. No absolutes. We're not saying the boiling point is this, the boiling point is that. Nor do I want you to go look them up. That's missing the whole point. Yes, we can go look it up, but that's not answering the question as to why. Okay, so which is polar? We went through that in the beginning. Ammonia is the polar species, whereas fluorine was nonpolar. Okay, which has the higher vapor pressure. Okay, so in a closed container containing ammonia and fluorine, which one would have the higher vapor pressure? And that would be the one with the lowest IMF, and which would be fluorine. Okay, there'd be more fluorine gas molecules in the closed container than ammonia. And then which, if there were liquids, okay, which would be the least viscous? And that will be, again, fluorine, because it has the weakest force. Okay. Now, these type of questions could be easily reversed. Instead of saying which is the stronger IMF, which is the weak IMF. Or number two, which has the higher boiling point. Just the questions can easily be reversed. Oh, yeah, I forgot the last one, which has the more surface tension. And that would be ammonia, because ammonia has the strongest intermolecular force, hydrogen bridging force. So those are a typical type of questions where you do a compare and contrast, not being asked specific amounts, just being told relative which is greater or less, A or B. Okay. And so to kind of summarize all this, you can say that as the IMF increases, viscosity increases. Okay. The boiling point increases and the surface tension increases. Okay. So as the IMF gets stronger, those three physical properties increase, which sounds counterintuitive, but if you think about it, it really isn't. The vapor pressure decreases because, again, the vapor pressure, the liquid phase is holding those molecules closer together and not allowing more of those molecules to go into the gas phase. Therefore, the vapor pressure drops. Okay, any questions? A couple of things about water, not much to say here. We kind of talked about it before. We did the Lewis dot structure. It has two bonding electron pairs and two lone pairs, if you recall the Lewis dot structure. That bond angle is much, much less than 109.5. Remember, 109.5 was pretty much the reference point, the benchmark of most chemicals. And then depending on the lone pairs in the central atom, that affected a bond angle. And because there's two lone pairs on oxygen, that bond angle really gets crushed. Water is very, very, very polar. It has very polar oxygen-hydrogen bonds. And we literally dissolve all ionic compounds. And, even the ones that are classified as insoluble, there's always water is probably classified, is thought as the universal solvent. It will dissolve literally everything. It just some things may take a little more time than others, but eventually it will dissolve. Okay. Um, and it mixes a lot with other polar material. Okay. Case in point, alcohol and water. It's a classic example. Alcohol is not water. It's an organic compound. Water is, I don't want to say it's not an organic compound, but they're two dissimilar species, but because of their polarness, both of them are polar, they will dissolve in each other. Okay, that's why you can have a mixed drink. Oil and water don't do that. Okay, they're both liquids, they don't mix because oil is non-polar and water is polar. Okay. All right, another aspect about water is strong, very strong hydrogen bridging force between molecules. Some of the properties, very polar, as I mentioned, high IMF, very low vapor pressure. Boiling point is 100 degrees Celsius and melting point is 0 degrees. High surface tension. And something unique about water is that when it freezes, the density is less, the density of ice is less than the density of liquid water. Okay, it's still water, it's just that ice is in the solid form and its density is much less. That's why your ice cubes float. And we went through this before. We determined that for equal amounts of volume of water, that what happens to the volume when you take 1 milliliter of water and you ice it, its volume increases during the icing freezing part. And so you don't have 1 milliliter, you have a 1+ milliliters of ice, and therefore the density ratio changes, okay, becomes less than 1, which makes it float because the density of ice is less than 1. 1 is water. And some interesting crystals of water. I mean, they're very symmetrical, very ordered. And for some reason, I'm told that the image of snowflakes are all, each one is completely different. Don't know if that's for sure, but pretty interesting crystals there. All right, so what I'm going to do now, which finish up this chapter, is we're going to talk about the heating curve. Now, most of the time we're dealing with water because that's the most common example that most everybody's familiar with. We know water is a solid ice, and then as we heat it up or the temperature goes up, it can be converted to liquid. And then if we continue to give energy into the system, we eventually cause that liquid to boil and go into the gas phase. Okay, and it's all about energy. And so if we look at a heating curve, we'll see temperature here on the y-axis, okay? And then the amount of energy we put into the system. And so if we start off with ice down here in the beginning, we got solid ice, and then we just slowly increase the temperature. We note the increase the amount of energy and note the temperature that we actually see changes occur to the physical property. Okay, a couple of things to notice that we have a very steep climb in the beginning, and then we end up with a plateau, and then we have a second climb, and then we have a second plateau, and then eventually all goes straight up to almost to infinity. Okay, so we have 2 plateaus here that something is going on there to give us a plateau, and regardless of how much energy we put in. So we put energy of this amount right here, it will continue to remain flat temperature-wise until we hit this point, and then it shoots up, okay? So for example, when next time you're boiling a pot of water to make some spaghetti, and you get that thing to boil, as soon as it boils, you get a thermometer, stick that thermometer in there. You'll see it. If it's a Celsius, it'd be 100 degrees Celsius or 212. And you can turn that heat up, and then wait a couple of minutes and measure the temperature. and you're going to find it's going to be 212 Fahrenheit or 100 degrees temperature. That temperature, no matter how much energy you put into that system, will remain constant. Okay, I'll explain that in more detail here in a second. All right, so what we have going on here, as I'll explain, you have in the beginning, and so we add heat, and we make a graph, so on and so forth. So this could be water, and so this could be 0 degrees, and this could be 100 degrees temperature. So we put energy into the system, there's a sharp rise of temperature, okay, as we go until it hits a plateau. Now, on that rise, we have basically all solid material until we hit the plateau. At the plateau, the solid is being converted to liquid, okay? When all the solid has been converted to liquid, then we have another jump in temperature, which is all liquid, until we hit a second plateau. At this second plateau is where the liquid now is being converted into gas or vapor. And that temperature remains constant on those plateaus, okay? We continue to fire it up, it's still not going to do anything temperature-wise until all of the liquid has been converted to gas, and then we get another increase, okay? So in these plateaus, what is happening there is this. As you put energy into the system, you are breaking up the intermolecular forces of whatever species you're heating up. You're breaking up those forces, okay, to cause that species to go from whatever phase to the next phase. And it's not going to increase no matter how much energy you put into the system. Its temperature is not going to change until all of that liquid, for example, gets converted to gas, or all of that solid gets converted to liquid. Okay? And so once you get that pot of water boiling, there's no need to turn that heat up. It's not going to get any hotter. It's going to stay at 100 degrees. So once you got it boiling, turn that heat down, let it continue to boil. Just add enough heat to maintain that boil, and you're good to go. And we'll save your money, save your either SRP or APS, save from having to pay more money. Okay. In fact, because of the heat capacity of water and how it acts, if you wanted to make, hard-boiled eggs, get that water to boil. Once you got the eggs in there and it's boiling like crazy, turn it off, and then wait your 10 minutes or so while there's enough energy in there in the solution that it will finish hard boiling, cooking your eggs. You don't have to continue to add heat to it and energy. All right, so let's clear this up. So the takeaway here is this: at the rises, at the slopes, that's where the physical state is constant until we hit the plateaus. And at plateaus, the temperature is constant because all of the energy you're putting into the system is being utilized to break up the intermolecular forces of whatever species you are heating, okay? Temperature remains constant. We are breaking up the IMF. We're not breaking bonds. I got to emphasize that. The temperature is not that high to break bonds. We are breaking up the intermolecular forces of the molecule, okay? All right. So that being the case, ladies, we lost one. We are done with this chapter. Congratulations. We will, let me see, 14. We will continue with 15, not next week, but the week after, and then probably finish 16 too, because 16 is not very long. We'll probably knock that out, and which leaves the following time for a a study day, self-study day. I will be here in class if you have any questions to get you ready for the final, and go from there. All right. All right. Let us stop.